Hey everyone, we're going to get started. So my name is Greg DeArment. I lead our production infrastructure group at Palantir Technologies, and I'm with Vlad, who's the technical lead on our cloud infrastructure team. And today we're going to spend some time talking about what happens when you run large Kubernetes clusters and you destroy every node every 48 hours. We'll talk about why Palantir chose to take an ephemeral approach to our infrastructure and how we run Kubernetes on it. Some of the technical challenges that come along with that, some of the solutions for solving those challenges, and some of the benefits that we've realized in taking this approach. Before I do, I want to briefly introduce Palantir for those who aren't familiar. Palantir is a software company. We were founded 15 or so years ago, and our mission has been to our purpose has been to improve the way the world's most important institutions use data to make decisions. A few examples of what I mean. Our software is the foundation of cyber defense systems for large institutions and entire nation states around the world. Our software is used in support of anti-terrorist missions in the West, from everything from intelligence operations to mission planning in the field. Ferrari uses our technology to make their Formula One cars faster and more efficient. If you look very closely, you can see our logo on the bottom right fender, which is pretty cool. Palantir and Airbus founded Skywise as a platform to improve the way the airline industry uses data to make air travel safer and more economical. Today, Skywise collects high-resolution telemetry from millions of sensors across the aircraft flying around the world and enable Airbus engineers and aircraft operators to use this data to root cause faults in flight and improve the way airlines operate the aircraft and the way they're manufactured. Palantir and Merck Pharmaceutical formed a joint partnership called Centropy last year, which is focused on enabling collaboration amongst medical researchers around the world towards improving the cancer treatments that they're working on. So how do we do all this? So Palantir software is used by our customers to integrate data and analyze data sets from across their enterprise, and is used by operators and decision makers to make better decisions using the data they have. And we do this by offering our customers two data platforms, Palantir Gotham and Palantir Foundry. So I want to talk a little bit about the infrastructure in which we run those platforms on behalf of our customers. So starting in 2013, we started offering our platforms as a platform as a service model to our customers, built on top of our first generation cloud architecture in AWS. The world has changed a lot since then. So 2 years after that or so, Kubernetes 1.0 came out in 2015. And as time went on, the needs of our data platform and the technology landscape continued to evolve. And so in late 2016, we started thinking about what would it mean to rebuild our cloud architecture for the future, and what would we change from our first generation architecture as we did that. And there was a number of things that were influencing our decisions and how we thought about the problem at the time. So the first of those was we started running into scaling limitations and hurdles in our in-place patching infrastructure that was largely built on top of Puppet. And we used Puppet to both patch the operating system, but also to roll out configuration changes for things like firewalls and so forth. And as our fleet continued to scale, our ability to make these changes in a timely manner became harder and harder. In 2015, there was a Zen hypervisor bug or two that led Amazon to need to reboot almost every EC2 instance in the entire world that was running HVM virtualization. And when this was announced, our infrastructure team panicked, as at the time we had a large number of instances that had been running for longer than a year. We had large volumes of data on the ephemeral volumes. And to be honest, we weren't sure what would happen when those instances got rebooted. We weren't sure if when they came back up, whether the data would still be there or whether the services that we were running on those hosts would be able to come back online. And at the time, Netflix and some others have been talking about chaos engineering and the benefits that they see from that for a number of years. Netflix talking about how they use Chaos Monkey and so forth. And so as we started thinking through what we wanted our infrastructure to look like in the future, a lot of this led us to asking what we thought at the time was a relatively straightforward question. Well, what if we just destroyed and rebuilt every host in every environment every 48 hours? If we did this, it would allow us to treat our infrastructure as immutable and ephemeral, which means we wouldn't need an in-place patching story, and a lot of the challenges that we had and the fears we had about rebooting instances would be solved because we'd be doing this constantly. So these conversations were happening at the end of 2016. Kubernetes had just hit version 1.5. Pet sets, now stateful sets, had just entered the platform. And it began to be believable that we could run all of our software at some point in time on top of Kubernetes. So in January of 2017, we started a team and an effort internally we called Rubik's. After the Rubik's Cubes, our CEO used to solve and leave on people's desks, and as a nod to Kubernetes. And Rubik's would be our effort to rebuild our infrastructure around Kubernetes, and in doing so, treat our infrastructure as ephemeral and destroy the hosts every 48 hours. So today, Rubik's is in production at the majority of our customer environments around the world. We run many Kubernetes clusters as part of this. We have environments on 9 AWS regions, I think soon to be 10, on 4 different continents. Across our fleet, we have more than 2,500 nodes at any given point in time. Oftentimes, it's above 3,000 as the environments scale up and down throughout the day. The clusters vary in size. We have clusters from tens of nodes to hundreds of nodes, our largest oftentimes reaching 1,200 or 1,300 nodes at the peak usage. And because we're destroying every host every 48 hours, it means that on a 24-hour period, we tend to touch about 10,000 EC2 instances between the standard destroying and rebuilding plus the auto-scaling. The primary workloads that we run on top of Kubernetes today are our distributed compute jobs, a lot of Apache Spark jobs. And because these pods tend to be relatively short-lived, we have very high pod churn across our cluster. So it's common that we'll see more than 1 million pods being run in the course of a 24-hour period. So I mentioned that we destroy these hosts all the time. I'll quickly touch on the framework we use for doing so. So we built a controller that's responsible for destroying and rebuilding hosts in every environment. It follows a relatively straightforward 3-step process. First step is to evaluate all of the EC2 instances that are running that are eligible for termination. We then take the eligible nodes and we apply a set of constraints to those to make sure that we don't do things like take all 3 etcd hosts out at once. That would be very bad. We down select all of the hosts that are eligible to the hosts that we can safely terminate, and then we send them to an actuator which will be responsible for marking the node as unschedulable, draining the pods, and so forth. So we've been doing this for 1.5 years or so. There have been a number of really great benefits that we've been able to see in running this in production, on top of the expected benefits of one would expect from chaos testing, chaos engineering, and so forth. The first of which was our ability to upgrade the cluster and mitigate critical vulnerabilities, or CVEs, has been greatly improved. And so I remember being at KubeCon in December last year in Seattle, and a number of people were talking about how they struggled to handle the number of CVEs or Linux security vulnerabilities that came out, how they handled upgrading Kubernetes as the hotfixes came out for those vulnerabilities. And 2 months later, they would have to handle the run C thing, whether they had known it at the time or not. And these conversations were the first thing that led me to realize how valuable our system is for mitigating this. Because for us, when the hotfixes came out for the vulnerabilities, it was simply a matter of us updating our AMI, and the same process that's running constantly would roll out the mitigation for us. And it was the thing that we didn't really think all that much about. It just happened. It was just any other day. The second big category of benefits we saw was, as we started trying to do auto-scaling, we realized that a large set of problems that one usually has to think about when you get to doing auto-scaling, we had already solved, because those problems are the same types of problems that you need to solve when you start treating your infrastructure as ephemeral. These are things like the host initialization time starts to really matter, your ability to do identity, like joining a domain, getting a certificate, those kinds of things, and your ability of handling networking connections gracefully as hosts come and go. So a lot of these challenges Vlad is going to talk about here in a few seconds, but for us, what it meant was by the time we got to auto-scaling, it was a relatively straightforward path for us to get it working. The third big category of benefits we saw was around security. And so for us, our ability to mitigate advanced persistent threat or a set of attacks that's usually where a malicious actor will use either social engineering or known vulnerability to land malware on a host in your network, and then use that as a jump-off point to move laterally through your environment. Our ability to mitigate these risks was greatly improved because now it is not only necessary for that malicious actor to compromise a host once, they must do this repeatedly because every host gets destroyed all the time. And so a malicious actor will need to continuously compromise an environment, and that behavior is hopefully easier to detect by your information security alerting and scanning and so forth. So there was a number of benefits. There was also a large number of challenges. Vlad was the tech lead on Rubix for the last 15 or 18 months. He was on the front lines of solving these problems, so I'm going to hand it over to him to talk through some of the technical challenges we ran into and some of the solutions we found.
Okay, folks, we're going to start with 4 challenges. First one is going to be about leader election services. Second one is going to be about cloud scaling. Third one, host boot up time and why does it matter when you run ephemeral infrastructure. And then fourth one is going to be about edge and container networking. So about consensus and leader election-based services, it's really important not to kill your leader in such a service when you're taking down hosts. For example, the most important service that we can think of is etcd. If you kill the etcd leader without any graceful termination, the API server is just going to 500 for a small period of time. In order to solve this, we took an approach where we introduced a framework that we call the pre-termination actions framework. Here, we deploy a binary that can either be a sidecar for a container or binary on the actual host. When the binary starts, it does a watch to the API server. It watches for its own node. And then when terminator selects the node to be terminated, adds a label. In our case, termination pending equals true. The binary is going to detect that that label was added and executes certain action. In etcd case, it's going to call the move leader endpoint. So then we can terminate the etcd leader gracefully. The API server is going to still serve requests happily in that time frame. Another service that we use in Rubix, it's HashiCorp Vault. We use it for secrets management and identity management. Vault is deployed as a 3-node cluster, 1 node being the primary and 2 other nodes being secondary nodes. Here we chose the same approach. Before killing the Vault leader, we just call it Stepdown endpoint. This is going to move the leadership of the Vault cluster to another node, and then we take down the Vault node itself, which now is a standby one in the cluster. Other 2 services that are present in the K8s ecosystem that are doing leader election are the controller manager and the scheduler. For these 2, we don't have any endpoint to call, and we found out that's just fine to kill them. They're basically running in the background, and they don't affect the overall health of the cluster for the 15-second time frame, which they do another leader election. So moving to cloud challenges, we found out that the cloud's not actually infinite, as we believed at the start. We had some problems when Amazon launched their 5th-generation instance types. We decided to use them the next week after they were launched. And in many scenarios, Amazon wouldn't even have 1 or 2 VMs to provision for us when we were doing the normal termination cycle. So we're detaching 1 machine from the autoscaling group and then waiting for the autoscaling group to bring another one up. Amazon would just ring out telling us that they don't have any capacity and we should just wait it out or swap the instance type. Around November last year, Amazon launched a feature for the autoscaling group service called multi-instance type autoscaling groups. This allows an operator to add more instance types to the launch template they're using for their autoscaling group. So for example, you can have 3 instance types over there, and if Amazon can't provision the first one for you, it's gonna move to the second one, and so forward. So this helped a lot in deploying Rubix to some of our bespoke Amazon regions where capacity wasn't always available. On top of not having capacity always, we found out that sometimes you're running on bad hardware. Usually we touch around 10,000 hosts per day. We terminate and bring another one up. This increases the chance that you land on bad hardware or hardware that Amazon wants to retire. This can be faulty hypervisors or hardware that Amazon wants to deprecate and exchange in their data centers. When across our fleet, we churn around 70,000 hosts per week. So we get approximately around 100 or 150 events across our fleet overall. In this case, we just changed or tweaked the Terminator code to detect these instances, like early on in the selection process, and then we just kill them without going through the normal pipeline. As a real-world example here, you can think that one of these instances that's running on bad hardware can be our API server. If that API server dies, all the clients are going to swap their connection to another healthy API server, and then they're just going to have a thundering herd problem. Moving next to host boot up time, when you're running ephemeral infrastructure, it's actually important to design for this problem. In our environment, our hosts live up to 48 hours, so spending a lot of time just setting up the host for doing actual work seems wasteful. In the previous cloud architecture, it would take us around 30 to 40 minutes to bring a host up, and that's just time left on the table, not running any user workload. On each host, we run 4 static pods for various admin purposes, like collecting logs or monitoring the host itself. When these static pods start, they need to pull their Docker image from a central Docker registry. In our case, we host a central one across all our environments. And we found out that during a day across our fleet, we are doing 32,000 image pulls just for starting the host. This meant that we're spending a lot of time on our gateway machines just doing network traffic, pulling these images over and over again. To overcome this problem, we deployed an in-VPC, in-cluster image registry, and all the image pulls are locally, they're way faster, and you're not oversubscribing the gateway machines for network traffic. Another flavor of a host boot up problem can be establishing the identity of the host itself. Usually when a host comes up, you need to talk to an external service to get either some credentials. In our case, we talk to Vault to get a certificate for the host that's signed for the host name itself. Back in the day, all our hosts were asking Vault directly to generate the certificate and the key. That's meant that the Vault cluster itself was generating that secret material and then passing it on to the host itself. This was putting a lot of load on the Vault cluster, just needing entropy and doing a lot of CPU cycles just to generate secret data. We swapped our approach to issue a CSR locally on the host and then passing the CSR to Vault to sign. This overall, I think, dropped the load on our biggest Vault cluster around 80%. Moving over to Ingress and Egress networking, our VPC design is pretty standard, follows a couple of industry standard practices. We deploy across 3 availability zones, and each AZ is configured the same. It has one subnet, which we call the DMZ subnet. In the subnet, we have our gateway machine that lives over there. And then all the other subnets have their default route pointing to these gateway machines. We kill the gateway machine normally, as would be another node in the cluster, so every 48 hours the host dies. This means that all the egress connections from the cluster itself to the outside world are going to be terminated. We need the way to reestablish connectivity, so we just reused our pre-termination actions framework to reach out to Amazon when the label was added to the gateway machine, scan the route tables, see the ones that will be invalidated, and then just move the route to another gateway machine from the other 2 AZs that are still alive and happy. This solved the egress problem, but then we had to solve the ingress problem, connections from the outside world coming inside the cluster. For this one, we opted, again, for a pre-termination action to inject a couple of IP table rules that were sending back TCP reset packets to existing connections to signal them that, hey, this host is going to die and need to connect to another one that's available. We also have another IP table rule that just refuses connections. So it forces the client to connect to another host that's available. So going to container networking, here the journey has been interesting so far. When we started Rubix, we were running Calico as our CNI plugin. We're running around Calico 2.5, and after some time, when we started scaling up and down our cluster, we found out that Calico didn't have enough IPs to allocate to pods. It was just erroring out saying that there are no more IPs available, but we didn't have that many pods in the system to just exhaust our full CIDR block. We did some investigation, and we found out that the etcd that Calico was using was full of data that was outdated. It had leases for IPs that weren't available anymore. Those pods were long killed. So to overcome this problem, we just deployed the K-cron job that every so often would walk the etcd key space, would validate if the data from etcd reflects the real world, and just nuke all the old IPs to give them back to Calico. Another problem that we encountered with Calico was around BGP route syncing. As our clusters grew in size, it would take around 5 to 6 minutes to bring a host up and running, so the K8s node to be ready in order to receive traffic. For those unaware, Calico implements full mesh for its BGP routing, so each node needs to establish a connection to each other node in the cluster. When we encountered this issue, we decided to look in the community to see what other alternatives are available for another CNI plugin, and we found out the Lyft CNI plugin. The main differences between these two is that the Lyft one doesn't use an overlay network as Calico does. It's doing native VPC routing, so every pod IP is an actual IP that Amazon knows about. So they're handed out from your VPC CIDR space. We swapped and started using the Lyft one, but this didn't come free. The main issue we encountered here is when we're doing somewhat bigger scale-up events, like bringing 300 to 400 nodes in service at the same time. The Lyft plugin would reach out to Amazon to allocate an ENI, then attach the ENI to the host, and then attach IPs to that ENI so pods can run on that host. So when you imagine doing 300 to 400 create and modify requests in parallel to Amazon, you would just get API rate limited. To fix this, we opted into swapping the order of operations. So now when a pod comes on the host, we allocate an ENI, and then we pre-allocate the IPs that we know we're going to use on that network interface. We usually know the pod density on each node that we run. So this is pretty fine up until now, but we realized after moving from Calico, we lost the ability to do network firewalling out of the box. So we decided to take it upon ourselves to build a solution for this. We built a solution in-house, but deploying it to larger clusters, we encountered certain scale problems, mostly around node and pod informers. The solution basically deploys an agent on every host, and the agent watches pods and watches nodes from the API server, but this puts a lot of pressure on the API server. Starts sending back a lot of information. The network traffic outbound from the API server is just insane. So we went back and looked around the community to see how people are solving this issue, and we found the Cilium project, and currently we're partnering with the folks from Cilium to bring all the good things from the Lyft CNI plugin, basically the ENI approach that the Lyft folks took, and we're going to start using the Lyft security stack as well in the future. I'm going to give it back to Greg for some key takeaways.
Thanks, Vlad. So, after doing this in production for about 18 months, we set out to solve a set of problems that we had at the time, thinking this would be a lot easier than it ended up being. And for us, this was a paradigm change in how we approach infrastructure. And with any paradigm change, you're going to run into a number of unexpected issues. And so we talked through some of the issues we ran into today. There were many, many more that we'd be happy to talk about if anyone is interested. For us, we found that investing in some relatively simple controllers or solutions like the pre-termination action framework allowed us to solve many of these problems in a repeatable way. And it took us probably longer to do that than we should have in retrospect. And so for anyone who's considering taking an ephemeral or immutable infrastructure approach and running Kubernetes on it, I'd encourage you to think about these things up front. We realized a lot of benefits by taking this approach. I think in retrospect, looking back over the last 2 years, knowing what we know today, we would definitely take a similar approach. We'd probably invest in a few areas a little bit earlier on in the process than we did, but we've been able to realize a lot of great benefits in doing this, though it didn't come without cost, as Vlad mentioned. So that's all we have. I'll point out that we have a booth in the vendor showroom. If you're interested in these topics or interested in learning more, we're happy to go into a lot more depth for anyone interested. We also are starting a blog series on Rubix and our adventures in Kubernetes so that others can learn from some of our failures over the last 2 years. So we published the first blog post last week, and there should be a number more coming up. And we're happy to turn it over for anyone who has questions. Thank you. Front.
I just have one question. When you're terminating the host, how do you handle long-running jobs that can't be terminated, let's say, in the next 5 hours? We have this problem because some of the jobs is really expensive to rerun and it can take a long time. Thank you.
That's a great question. So this is one of the first problems we ran into. So we run a lot of Spark applications, and so anyone who's familiar with Spark, you have a driver and you have several executors. The cost of destroying an executor, you may have to do a little bit of repeat work. The cost of destroying a driver, you have to start the entire job over. And so many of these Spark applications can run for very, very long periods of time. And so we built a framework for our stateful services as well, where we add essentially like a health endpoint, some notion of health on top of readiness and liveness. And for drivers, we let them say, please defer draining me, please defer killing me. And so our termination framework actually takes this into account. So as we're filtering out all of the eligible nodes into only the ones that we can actually terminate, we allow some pods to defer termination for up to 24 hours. And so in theory, every host only lives 48 hours, but we allow it a 24-hour grace period if necessary before we terminate it forcefully. So some hosts can live up to 72 hours, but we basically take this into account to try to avoid that with some limits. Does that make sense? Wonderful. Any other questions? In front? Here, let me bring the mic.
Thank you. Do you have similar tips and tricks for ephemeral storages?
Unfortunately, no. We've run into a couple problems with storage over time. So most of the storage we use today is ephemeral. So Spark jobs will spill to disk and so forth, but it's like ephemeral data, so it's fine. For running etcd, when the etcd hosts get terminated, we built something kind of similar to persistent volume claims, where we will detach the EBS volume from the old host and attach it to the new host that comes up that's going to run etcd, so that the data will follow etcd around. We run etcd as a static pod, but obviously we can't run it as a stateful set since it underpins the API server. So there are some tricks like that we've done, which we've had to invest in that work up front. We don't run that many stateful sets today. We tried a year ago and ran into some issues with auto-scaling groups having capacity that comes up in the wrong availability zone. Those issues have since been fixed, I think, in Kate's 111 or 112. And so we'll pick those changes up when we return to that work. But other than treating etcd EBS volumes, like moving them around, we don't really have any other tricks other than that.
What do your pipelines look like for building the images?
Yeah, I can take that one. So we build a foundation AMI that's just basically running Packer on top of Ubuntu Bionic. And from there, we publish that AMI internally. And then every type of host that we run in Rubix, we have, I think, 5 of them. So gateway machines are a bit special. etcd, it's a bit special. masters, which are API server, controller manager, scheduler, and then just like the plain worker. So we rebake the foundation AMI, installing like different packages that we need, or seeding different Docker images, and then we just like publish that. And our Terraform code, when it runs, finds these like certain type of AMIs and just launches them. So as a bluff, it's just running Packer on top of Ubuntu, and then like repackaging it internally afterwards.
First of all, great job. Second, the question, in your experience, most of the effort has been spent on the ephemeral model or at the scale? Or both, or the ephemeral model becomes so complicated due to the scale?
So the question is, are the issues that we ran into mostly due to the ephemeral nature or because of the scale? Is that correct?
It's like a mix here. For example, the ephemerality problem, we found it, for example, in K8s is when Amazon reuses IPs from the VPC. Like a new node would come up with the same IP, and then the controller manager would detect that it has the same IP and would just kill the node from K8s itself. So basically, a new machine would hijack the identity of an old one, and then the controller manager would like delete the node, so you're stuck with just an EC2 node running a kubelet, but the kubelet wouldn't re-register itself. So that's like one form of ephemerality problem. Scale problem, I think what did we hit in the scale problem? It's like in the networking stack, like the networking challenges that I discussed with Calico. Other than that, just when we launch workloads and all of them try to talk to the API server, that's mostly something that we need to take care of on our end rather than K8's specific problem. Can you think of any other ephemerality?
So I think the edge networking challenges that Vlad talked about, like ingress and egress from the cluster, those are largely based on like the ephemeral nature of them. It's, it has little to do with scale itself. So I think anyone who does this, who also has single entry points and egress points in their environment, will also have to face. Other networking, like the container networking challenges, were some mix, and it sort of changed over time. So Calico, it was kind of the ephemeral nature. The lift stuff we run into today is more related to scale, though the problems are exacerbated by the fact that there's so much change in the environment. It just makes it harder. And then, it's sort of a mix. I would say the first year it was all ephemeral stuff. The last year it's been a mix of scale and ephemeral challenges.
Hello, very good talk, and I do applaud your bold approach into this. I can only imagine meetings and how they went. So my question is related with cloud provider bugs. It sounds like your approach in the life cycle of a machine can actually propagate them instead of contain them into one, let's say, or two instances. And how does this look like in the monitoring and alerting for you?
So I think the question is, how do the challenges we see, how do we handle them in like network or the monitoring and alerting? Is that right? Do you want to take that one, or you want me to?
Go ahead.
So I think one of the big challenges for us with our first generation cloud was we had very rigid rules for monitoring and alerting. So when a host would disappear, for instance, it would like ring all the bells, so we couldn't auto scale on our first generation cloud. And the second generation one, with Rubix, we've moved toward sort of we care a lot less about every host, and we care more about an auto-scaling group. And so we will alert when the number of instances in an auto-scaling group drops below some threshold, but we don't care about a given host. And so if a host comes up and it's bad, like there's Amazon hardware issues, we just kill it. It's just like we don't even care, just like kill it, move on with our lives. And it's only once the number of those problems crosses some threshold that we start worrying about it. Does it make sense? This is true largely for like the large pools of worker nodes we run. When one of the routers becomes unhealthy, we've had issues over time where before the pre-termination action framework, we would have an issue where if the router became bad, your only egress point from the availability zone would be down, so you'd lose the entire AZ. And so there were some issues like that that we had to work through early on in order to make the alerting work correct. But today we take much more of a cattle versus pets approach to the problem.
You mentioned that you run the Docker image registry locally on the VPC to handle the image pull problem. Can you describe in more detail how you manage images, how many registries you use, how do you push images?
Yeah, I think I can take this one. So usually our developers build the images internally, and we use Artifactory, JFrog Artifactory internally. So we publish those in our CorpNet registry. And then on top of that, we have a solution that allows external clusters from the internet to just authenticate with that corporate network registry to pull the images. And in our VPC on our gateway machines, we deploy a cache registry, basically. So when the gateway machine comes up, its cache is going to be empty for the moment. All the clients are going to reach the cache. The cache is going to reach upstream. It's going to pull all the images, and then all the images are going to be cached on the routers. And it's going to happen across all 3 AZs when those machines cycle, basically. Now we're looking into storing actually the cache on EBS drives and do the same dance as we do it with etcd. It's going to follow the node when it comes up and down, just to sustain unavailability of the central registry itself.
Today, it's also helpful that we have a relatively few number of images that are run in our environment. The vast majority of pods run one of 5 Spark images, for instance. And so once the cache forms quite quickly, and it evolves slowly over time. And so we get a lot of value out of that. As we run more and more of our infrastructure, more and more of our microservices in the environment, we expect that to go up some, and that will have a higher rate of churn. But cool. I suspect we're probably out of time, so we'll do one more question. And then for anyone else who's interested, you find us here after or come to our booth. So we'll do the back corner.
Hi, I'm Junaid. So I have a question related to DNS. Have you had any issues with your DNS while at scale, because you have 800 plus nodes cluster? So did you face any issues with?
To be frank here, I don't think we paid close attention to DNS issues. Currently, we are running core DNS and all the practices that the community upstream opened to the world. I think we've hit a couple of problems with the Amazon VPC DNS resolver rate limiting us because we're doing so many queries, but I suspect those are just because of the ndots problem, and the rest people are hitting. So we're planning to deploy the local node cache to not do so many queries upstream and just hit the local cache. But other than that, that's it in this DNS space that we hit.
Cool. Thanks everyone for coming. We're here after if anyone has any other questions. Thank you.
Yeah.